Take it away. Find my clicker. Just want to start by thanking our sponsors. It's great that it's so cheap to come along. These free ticket, well, almost free, $60 tickets, but it's quite expensive to put the thing on. So that's where we really need to say a big thanks to our sponsors. And this room has its own sponsor, Software One. So thank you, Software One. Tony Hoare invented the null reference to make programming better. And 40 years later, he said it was a $1 billion mistake. We'll look at what he meant in this talk, but mainly I want to ask another question. Has the software industry made other $1 billion mistakes? Are we making new ones right now? This talk is an exploration of those questions, and I'm going to propose some additional members to the $1 billion mistake club. But to start with, I want to get us in the right frame of mind for thinking about our mistakes as an industry. I thought I'd do that by recalling some headlines from within living memory. In 1996, the Ariane 5 Rocket 501 exploded, destroying itself and its payload of painstakingly developed research satellites, totaling $500 million in losses. The cause was a simple numeric overflow in the guidance code. For a while, in 2015, anyone could crash an iPhone just by sending it a message, due to a bug in the character handling code. In 1985, patients were injured, in some cases fatally, after being hit with huge doses of radiation from a machine called the Therac-25. The machine's software had a race condition that wasn't detected in tests, but it occurred in real-world use. The crypto industry has seen not only huge frauds like FTX, but also huge investor losses caused by software bugs in code that runs on blockchains such as Ethereum. Just this year, in 2024, a bad CrowdStrike update caused numerous flights to be grounded and brought banks and retailers to a standstill, with total losses estimated at over $5 billion because of a line of code that read past the end of an array. The organisation CISQ released a report in 2022 estimating that overall, software problems cost over $2 trillion in losses per year, and that's just in the US alone. So it seems the message so far is our software is bad and we should feel bad. But here's something that will hopefully cheer you up. We're not the only ones making $1 billion mistakes. When you're feeling bad about the failures in your life, what's more comforting than looking at the even bigger failures of your friends and neighbours? So let's just go there briefly, just for fun, and hopefully that'll get us in the mood to spend the rest of this talk casting a critical eye at our own mistakes. There's lots of good examples in the finance industry. I'll just mention one. In 2022, a Citigroup trader put a big number in the wrong field and pressed enter. European markets went into a selling frenzy. The total losses, which included a massive fine, wiped out 2 years of the trading desk's revenue. But at least no one was hurt, right? Which brings us to this guy. Thomas Midgley invented leaded fuel to make engines run smoother, which then was pumped into the air by cars for decades. Lead is a potent neurotoxin. One study found it knocked 6 IQ points off people born in the 1960s and 70s. Midgley then went on to develop chlorofluorocarbons, commonly called CFCs, for use as refrigerants, which cause the hole in the ozone layer. That's one reason why 2/3 of Australians will be diagnosed with cancer, skin cancer, in our lifetime. One historian said that Thomas Midgley Jr. has had more adverse impact on the atmosphere than any other single organism in Earth's history. So in the grand scheme of things, maybe a $1 billion mistake here or there isn't so unexpected. But let's get back to our original question. Are there other $1 billion mistakes? To answer this, let's do some napkin maths. The infographic that I'm showing you here is from that 2022 report that I mentioned. It's called the CPQS report, which stands for the cost of poor quality software. And you can see it's a bit messy, but it boils down to this. We still don't know how to create software without also creating lots of extra costs in the forms of legacy, tech debt, hacks, defects. In theory, at least, these costs are avoidable in the sense that if we figure out how to create good quality software, we wouldn't have to pay these costs. I don't want to be unrealistic. I don't think we'll ever have perfect software, and some of these costs are really human costs, like social engineering. or just plain bad management, which isn't unique to the software industry. But let's just say that both this report, the CPQS, and Tony Hoare's billion-dollar mistake, let's just say that they got their numbers right to within an order of magnitude. Then a simplified view would look something like this. Seeing it this way, it's hard to avoid the conclusion that there must be other billion-dollar mistakes out there, and probably quite a lot of them. But before we start looking for candidates, there's just one more thing I want to clarify. Those bad headlines in my introduction, they looked at mistakes at the point where things went obviously wrong. But in this talk, I'm really only interested in the driving factors that cause these instances of mistakes. As an analogy, imagine a product recall for a car where there'd been a lot of incidents where a wheel had fallen off. The car maker points out that in all these incidents, the driver had hit a pothole or the curb. So the problem is the driver, not the car. But the regulator states that a car should be built to deal with known hazards like that, and it holds the car maker liable for the cost of all the accidents and the redesign of the car. So the poor car design was the driving factor, pardon the pun, behind all these costly accidents. In software, we can also find driving factors behind all our costly accidents. And the one I'm particularly interested in, which is unique to our industry, is programming language design. Tony Hoare, the inventor of null references, pointed to this in the same talk where he said null was a mistake. He said, a programming language designer should be responsible for the mistakes made by programmers using the language. So programming language design will be a lot of my focus in this talk. Another apt phrase for this would be prevention is better than cure. So here's an overview of the mistakes I'm going to explore today. If this was a club, the billion-dollar mistake club, the first three would be retired members, things that we either fixed or we just avoided altogether because we caught them early. Then I've got a couple of what I'm calling rejected members of the club. We'll get to that. And then we've got some current members of the club, and then we'll look at potential new applicants. So let's start with null references, the namesake of this talk. And here's Sir Tony Hoare in 2009 giving that talk and looking quite ashamed of himself. I think he's actually just looking at his speaker notes, but that's, I thought, a good screen grab for this talk. So what did he do exactly and why? So let's first of all start with looking at the case for null references. Let's just say that we've got the need for some sort of data structure with nodes which point to another node, and we need to be able to create cycles. So in my simple example, at the bottom here, we want to have node A pointing to B, B to C, C back to A. But in order to construct a node, we need to give it a reference to the next node. So when we try to construct A, we don't have a reference to B yet, so we can't construct that, but we could maybe construct B first so that we can construct A, but then we need C first and C needs A. So one way or the other, there's no way to construct this with valid references. That's something that Tony Hoare was trying to solve, and he realized, well, what if we make it that null can be a valid value wherever a reference could appear? What we could do then is we could assign null to a reference to mean this is missing or it's not initialized yet, and that's what we've done here in this example circled. Now the problem goes away because we can just construct our nodes A, B, and C, and then we can actually assign the references from each to the next, and the problem's solved. Great. So what's the billion-dollar mistake? Well, to illustrate that, here's some code from a fictional country's national defense system. This was a huge multi-team effort. Here's some of Team A's code. It's pretty straightforward. If the country's under attack, we obtain a target and we launch nukes at it. Unfortunately, the country was attacked, and rather than defending the country, this program crashed with a null reference error, and half the country was destroyed. An investigation was conducted, presumably by the other half, to find out what went wrong. Team B shared their radar tracking routines, and Team C shared their launch routines, and the source of the error was now pretty obvious. Obtain target, the function there, since version 2 could now return a null target because now it handles multiple targets. So, if you're going to ask for a single target, there needs to be some sort of sentinel value to tell you, oh no, you need to go and call the other thing. So they changed that to return null to support this new version. But the launch code of Team C assumed that the target was always defined. That assumption worked fine in version 1, but it now crashed the system. So Team B, they refused to take the blame because technically returning null was always allowed. It's always a valid value for references. So it wasn't a breaking change. And they clearly documented it. They said Team C should have been checking for null all along. But Team C refused to take the blame. They're standing by the obvious logic that it's pointless to launch at a null target, And furthermore, all their unit tests with their mock targets were all passing at the time of the incident. The conclusion of the final report was that the programming language itself was to blame, because there was no way to capture critical requirements like the possibility of null in the programming code itself in a way that could be automatically checked. This critical information was conveyed only in comments, and getting it right was a manual job left up to human attention. To sum up null references, basically there's a problem, a solution, consequences, and alternatives, and I'm going to have a slide like this for all of these. So in this case, he was just trying to improve the safety and ergonomics of references. Null solved a problem, and it was easy to implement. But the consequences, which became apparent decades later, was that the ability for null to be a valid value everywhere just massively increased the space of possible programs that were acceptable to the compiler, and it made bad outcomes easier to create. And there are modern alternatives, so we don't really have to deal with this. And this is really a talk about problems, not solutions. But just so you know, there's things like non-nullable references, option types, union types, and static control flow analysis. So that's null references. I'm going to move on to another retired member of the billion-dollar mistake club now, and that's the GOTO statement. GOTO would certainly have become a billion-dollar mistake if it hadn't been apprehended early. Most of us probably don't even see GOTO statements anymore, but we've probably heard of this very famous paper by Edgar Dijkstra called GOTO Statement Considered Harmful, which is the progenitor of all the subsequent considered harmful papers. This is the entire paper on this slide. It's not meant to be readable. I just wanted to show you how short it was, considering the enormous changes it brought about in how we program today. His essential argument, which I've highlighted here, was about human fallibility and how better programming language concepts could prevent whole classes of common mistakes. He says here in these highlighted bits, "For a number of years, I've been familiar with the observation that the quality of programmers is a decreasing function of the density of GOTO statements in the programs they produce. Our intellectual powers are rather geared to master static relations, and our powers to visualize processes evolving in time are relatively poorly developed. For that reason, we should do our utmost to shorten the conceptual gap between the static program and the dynamic process, to make the correspondence between the program spread out in text space and the process spread out in time as trivial as possible." So here's an example, and I got ChatGPT to generate basically two examples of the bubble sort algorithm. They're both in a dialect of BASIC. So the one on the left is using line numbers on every line and GOTO statements. And the GOTO statement is pretty easy to implement, right? Every line is numbered. If you come across a GOTO statement that says, go to line 70, then it just jumps to line 70 and continues from there. But I've also annotated that with some arrows showing you where the control flow goes, and it can get quite confusing. If you basically want to understand what the loops, what are the loops in the bubble sort? What are the conditions? Where are the guards? Where's this? You've really got to run this in your head. It's quite easy to get wrong. And in fact, ChatGPT got it wrong. There's a bug in that code. And I thought, you know what, I'm going to leave that bug in there because it shows how easy it is to just get these things wrong. And well done if you notice on line 60 that there's actually an if statement there that effectively goes to line 70 in both the true and the false condition. What's interesting is that you could not even express that in structured programming, which is the version on the right, which is what Dijkstra was proposing that we switch to. You couldn't create an if block that was both the true and the false block. So GOTO works. It's very, very powerful, in fact. But structured programming on the right is so ubiquitous now that it's pretty much all we know. We don't even call it structured programming. We just call it programming. The summary for GOTO is that programs need to be able to express control flow. And GOTO solved all of this in one statement, and it was easy to implement. But consequences. This is a familiar one. Its flexibility allowed a huge space of invalid programs that couldn't easily be detected because they're semantically valid. They're valid programs, they're just not the program you wanted. They're one with some bugs in them. There's alternatives now. That's why we don't generally even hear of GOTO anymore. And the one is structured programming. You just have these blocks which represent loops and conditionals. So we've lost power. We've lost power to express things using GOTO, but actually I don't think most of us miss that power. All right, this one's going to be a bit obscure, this one. like GOTO, it's now mostly forgotten, dynamic scope. But this was the way variable lookup worked in early versions of Lisp and in a few other places. And I think if this had have taken off, it would have become another member of the billion-dollar club of mistakes. So again, I've got some code on the left and the right, and on the left, this is just plain JavaScript using static scope, which, whether you realize it or not, is basically how we always scope everything in pretty much all languages now. What you'll notice is that there's 3 different declarations of a variable called a. One is at the top in global scope, and there's one declared in the function g, and there's one declared in the main function. They have different values, 1, 2, and 3. But whenever you call the function, so at the bottom there, when we call f, what does it print? It prints 1. When you call g, what does it print? It prints 1. So most of you should know why that is. If you look at the function f, you're trying to work out what does that a refer to in the function f. And the rule is quite simple. You just look at the text of the code. You don't need to run this in your head. You just look at the text. Is there a local declaration of a in that function f? No, there's not. So you go to the outer declaration, the lexical scope outside, which is the global. It's the a equals 1, so that's what you print. And it doesn't matter if you call it from g. G calls f, but you just do the same logic. Is there a local a in f? No, there isn't. Is there one in the global scope? Yes, there is, so we print 1. Now, on the right, this is a demo of dynamic scope, and I've just used JavaScript syntax, but the concept applies. Here, at the bottom, if you called f from main, it would print 3, and if you called g, which calls f, you'd now get 2 printed. So what's happening here? Well, we start the same. If you're looking at the print statement in function f, we start the same way. We say, is there a local variable a? No, there isn't. So is there a local a in my caller? Well, where were we called from? We were called from main. So yeah, there is, and the value is 3, so it prints 3. But if you call f via g, when f says, is there an a in my caller, now the caller is a different function. It's g, and the value of a is 2, so it prints 2. This is really, really confusing because basically the behavior of a function depends on the call path that the program took to get to it. It'll behave differently depending on how it... So the question is, why would you ever even want this? Why was this ever a good idea? Well, it was probably, we didn't know how to do these things at first, so we experimented with different things. But also, here's a case. In JavaScript, let's just say that we had some application that was signing up users, and you pass in a registration form, and it's like, just check that they're the right age, and if so, we'll store their credentials and we'll send them an email. But the developer is like, there's a lot of repetition of this variable registration form. It's too long. Like, can we shorten this? And he's like, remember there's this thing in JavaScript called the with keyword. So you can still do this in all browsers today. It's just in non-strict mode, which is quite hard to access. But yeah, you can basically pass in your object to the with statement, and inside that block, any property that is inside that object is brought into the local scope inside that with statement. So now we can just say age. We just refer to age. We can refer to the username, the password, and the email, and they all come from that object. And that is dynamic scope. It's the same thing. But it seems quite useful. That could be a good case for it. Why did we get rid of the with statement? Well, because it's extremely... Remember that it's hard to reason about. If a hacker was able to get hold of this registration form, they could put a store creds property on that. And now you're not calling the store creds that you think you're calling their store creds, because when we work out what does store creds refer to, in dynamic scope here, it goes, there's one on your object, so that's the one that I'll call. The behavior of that function totally depends on dynamic factors that you can't predict from just looking at the code. That's really dangerous, and that's why with has basically been banished. So in summary, again, code, there's a problem, right? It needs access to non-local variables. There was these couple of solutions that people came up with. They seemed kind of both good at the time. But it quickly became noted that dynamic scope is complicated and confusing because functions behave differently depending on who calls them. And generally the alternative is we just got rid of dynamic scope and we only use lexical scope, with a couple of notable exceptions like C and C# macros. All right, let's take a break from looking at code. I want to look now at a couple of historical computing ideas that were not pursued. All we can ask here is, what if? We'll never know what mistakes we would have made on these paths, but I think they're just fascinating historical curiosities. If nothing else, you might pick up a bit of obscure trivia you can wow people with at the after party. The first one is the Russian computer called Saturn from 1958, pictured here. Something we take for granted today is that computers represent everything using binary numbers, but that wasn't always so. This computer did not have bits, it had trits. Instead of on and off, or 1 and 0, each trit had 3 possible states, 0, 1, and -1. Saturn represented everything in balanced ternary notation. Multiples of 3 came up elsewhere as well. The computer had 81 words of memory, and each word held 18 trits. With hindsight, we might say that this was a costly waste, since pretty much everything is binary today and alternative systems lost, so just a waste of time and money. But that was not obvious at the time. I discovered Saturn while reading Donald Knuth's section on number systems in the art of computer programming. He calls balanced ternary notation perhaps the prettiest number system of all, and shows how many numerical operations are simpler with trits than they are with bits. Knuth even suggests that ternary computing could make a comeback someday because of its nice mathematical properties, when, in his words, the flip-flop will be replaced by the flip-flap-flop. If that happens, then our descendants might look at the few decades when binary computers ruled the earth as the wasteful aberration. But I think don't hold your breath on that. The other historical marvel I want to mention here is the analytical engine, designed by Charles Babbage in the 1830s. At the time, numerical calculations in engineering, banking, and other fields relied on tables of numbers that often had errors in them because they were made by humans. That theme again. Babbage had an idea to make these calculations 100% reliable by automating the whole process. He wanted to build a calculating machine. But the kind of calculations varied, so he wanted to build a general-purpose calculating machine that could be programmed for any task. Does that sound like a familiar concept? He did design this machine, and it was a completely mechanical design. It was never built in his lifetime, but a partial replica was built, and part of that is shown here, and that it was built in the 1990s, and it weighed about 5 tons. I don't think we truly appreciate how astounding Babbage's inventiveness was. Here are some of the concepts, all familiar to us today, that he figured out 100 years before the first electronic computers. His design was Turing complete in an age when we didn't even know what that meant. There might even be $1 billion mistake here. And that is that his ideas were basically ignored and forgotten, and they had to be reinvented by other people 100 years later. What if his ideas had gotten more attention and traction back in the 19th century? Who knows? Maybe living standards might have shot up a lot earlier. Maybe some of these retro futuristic pictures would have been realised. We might even have flying cars by now. All right, let's come back to modern times. And now we've moved on to current members of the $1 Billion Mistake Club. The first one I want to talk about is concurrency. Many years ago, as a student, I had a go at writing a GUI application to draw fractals, like the one at the bottom in the centre here. The results were not what I expected. The renderer actually worked great, but while it was rendering, everything else on the computer ground to a halt. The music stopped playing, the mouse pointer even stopped moving. It took me a while to work out what I was doing wrong. To cut a long story short, I was programming this on Windows 3.1, which was single-threaded and used cooperative threading. When you write an application for Windows 3.1, your code is expected to explicitly yield control back to the operating system after very short intervals of computation. Otherwise, nothing else gets a chance to run. One badly written program, like my fractal renderer, would grind the entire system to a halt. Modern operating systems use a different model called preemptive threading. Each application can have one or more threads to run its code, and the operating system schedules these threads onto the available CPU cores. This means truly parallel computing on multi-core machines. On a typical running computer, there might be hundreds of threads, but only several CPU cores. So the operating system gives each one a short slice of execution time and then puts it to sleep, and resumes it later when the other threads have had their slice of execution time. This all happens very fast, and it gives the appearance of everything running smoothly all at once, even in the presence of CPU hogging applications like my fractal renderer. This model of preemptive threading obviously had to be supported in at least some programming languages, especially systems languages like C and C++. But it also became the default concurrency model for higher level languages like Java and C# when they were released. Some years later, a cool new thing arrived called Node.js. It proudly advertised the efficiency benefits of its single-threaded concurrency model. I was interested in trying it out, but the more I looked at it, the more I realized it was basically the same cooperative threading approach used in Windows 3.1. Concurrency with a single thread, and if something hogs that thread, everything just stops. But what was interesting were the performance benchmarks. They often showed Node's single thread outperforming enterprise-scale multi-threaded solutions like Spring on the JVM and ASP.NET. And here's an example of a benchmark from 2013, Tech Empower benchmarks. It turns out that using preemptive threading in an application can be pretty inefficient. Operating system threads are heavy resources, and switching between them has CPU costs. They also spend a lot of their time blocked, doing nothing. Today, Windows 3.1 style cooperative concurrency seems to be in all the cool languages and frameworks. It might go under various names like coroutines, green threads, asynchronous APIs, and non-blocking I/O, but they are typically all based on cooperative rather than preemptive concurrency. Spring itself now proudly advertises its asynchronous non-blocking architecture. What was a mistake for operating system concurrency now looks like a great idea for application concurrency, and the inverse is true as well. What was great for the operating system doesn't look so good inside an application. But that's not even the biggest problem with preemptive threading in applications. The much costlier problem has been the killer concurrency combo. On their own, they might be okay, but when you put these together, well, the threading model that C and C++, Java and C# and others have adopted has these two parts. Multiple threads in the same application can execute simultaneously. And all those threads have access to the same application data. To see why this is an issue, let's look at an example. Here's two stack implementations. The one on the left runs on the JVM, and it has bugs that could cause a major issue in production. The one on the right runs in Node, and it's fine. There's nothing different in the code aside from minor syntactic differences, but that's kind of the problem. Suppose a thread running the Java code on the left gets suspended at one of these orange arrows that I've highlighted. It's basically between two critical parts of doing a push or a pop. At that point, the stack is actually in an inconsistent state, despite being fully encapsulated in a class. So, for example, we're in the middle of this push method. What we've done so far is that we've put our item into the array, but we haven't changed the size of the array. So what if a second thread, let's just say that first thread is put to sleep now, and the second thread wakes up and it also tries to push something onto this stack. Well, it's going to become invalid because it's going to push its own thing and increment, then the other one's going to wake up and it's going to increment, and there's going to be one lost update and one random piece of data that shouldn't be there. So depending on what the application is doing, the results could vary from a minor bug to a major corruption of data. This is called a race condition. On the right, the one that runs in Node, there's no possibility for the stack to be observed in an inconsistent state because this code executes cooperatively, running until it yields control. Since it doesn't yield control in the middle of the push or the pop operation, nothing can ever observe an inconsistent state. Going back to the one on the left, there's fixes for this. To fix that issue in the preemptively threaded environment, the programmer would need to consider where race conditions can occur in their code. And this is already a big ask. It requires a lot of careful analysis. Race conditions are often only detected when they show up as a bug. Even then, these bugs are notoriously hard to reproduce because they can depend on very minute differences in timing. Once the critical section of code has been identified, the programmer can add explicit locks like I've done here on the right. And that's actually going to cause threads to block when another thread is already accessing that section of code. So that means that we won't have anything be able to observe inconsistent state. Or, here's another alternative, you could just use the magic synchronized keyword. Why doesn't Java just add this onto all your methods automatically? Well, because the whole point of concurrent programs is to run fast and have high throughput. Locks have a performance cost, and synchronization explicitly eliminates concurrency. So they need to be placed strategically. And the burden of figuring all this out is placed on the programmer. It's no wonder that race conditions are another common source of costly bugs. And given that the cooperative alternative is both fast and it eliminated many sources of race conditions, it looks in hindsight like $1 billion mistake. So again, there's a problem. We've got all these cores. We need to use them efficiently. The solution, well, the operating system does it that way. Let's do it the same. We'll just have preemptive threading, and all those threads can access the same state. But then the consequences, you put those two things together and you get race conditions. And what's the alternative? Well, there's examples of it, right? Cooperative threading instead of preemptive, and maybe don't use mutable shared state if you can get away with it. And also, if you're stuck in an environment where you do have this kind of problem, you've got to use locks. You've just got to do the work. Okay, last one from this section, manual memory management. If everyone in this room had their own list of billion-dollar programming mistakes, I suspect memory management would crop up on a lot of those lists. And for good reason, right? It's one we keep hearing about when a vulnerability is discovered. And they have really cool names too, like Heartbleed, WannaCry, Cloudbleed. Let's cut right to the heart of the problem with this one. This is basically a C and C++ thing. So C's approach to memory management can be summed up in two parts. Number one, vest all power and trust in the programmer. And number two, keep the compiler really simple. So I've got a basic example here. First thing that we're doing in this example is we're declaring a kind of data type that we're going to use in our things. Just a dummy example. So here our data type just has a string called a name. But a string here is represented as a pointer to memory. And we're just telling C that pointer to memory represents a list of characters. And we hope that that's what there is in there. And by the way, how would you know how long the string was that was in there? It's not referenced there, right? You literally have to go in and look at all the bytes, like follow that pointer, look at all the bytes and look for a null byte at the end or a 0 byte at the end. Hopefully it's there. Otherwise you'll read right past the end of your string and into some other data structure, and who knows, maybe you even get a segfault. Okay, we've got our structure. The first thing that we're going to do in our little program here is we're going to create an instance of this structure. And for that, we have to allocate our own memory for our string. So we're calling malloc to do that, to get 16 bytes of memory. And then we are telling C, this raw pointer that we've just allocated, I want to treat it like it's an array of characters. And now we can just copy some data into there. A few things to be careful of here. I didn't do any error handling here. Malloc can return 0. I haven't checked for that here, so we would just dereference that. That'd be another sort of like a null reference error. But here you're not going to get an exception. You're possibly just going to get a segfault or who knows. Also be very, very careful when you copy your string into here that your string isn't longer than the amount of memory you allocated, because you'll just write straight off the end of the array, maybe another segfault, maybe you'll just corrupt some other data structure in your memory. Okay, if you get past that, what we're doing now is we're going to make a copy of our structure. So we're going from copying from our source structure to our dest structure. And we're going to fully exploit the power of pointers here by just having a helper function to copy structures that all it does, you just pass it these like raw pointers and a length, and it'll just copy whatever it finds at those pointers from one to the other. So we're just copying our structure, but note that that basically means it's a shallow copy. And in particular, we haven't copied the full string from one to the other. We've just copied the pointer to the string. So we're done with our first structure now. We allocated that memory ourselves manually, so we have to remember to deallocate it manually. If you forget this step, you've got a memory leak. And finally, we've still got our dest structure, so let's print out the name that we had there. And now your thing explodes because that pointer to that name is the one that we just freed on the previous step. We'd aliased the pointer. So yes, there's basically a minefield of things that you've got to get right. And what's the consequences of getting it wrong? Well, it varies from mild to catastrophic, as a lot of incidents show. And where is the burden of getting all this right? Well, it's placed firmly on the shoulders of the human programmer. This hasn't worked out well. If you add up all the costs of all the CVEs in terms of losses to hackers, costs of remediation, as well as the costs of all the tooling and developer time spent on this, it's probably more of $1 trillion than $1 billion problem. Even Barney Strastrup here, the inventor of C++, might agree. He said, C makes it easy to shoot yourself in the foot. C++ makes it harder, but when you do, it blows your whole leg off. Oops. Perhaps the most interesting question here is, why are C and C++ still in such common usage? Is it because there are no good alternatives? Well, there is one alternative that I suspect most of us rely on so much that we don't even think about it. And that's automatic memory management, aka garbage collection. In languages like Java and C#, when we need to create an instance of an invoice or a hash map, we just say new invoice or new hash map, and that's that. We don't write any code to deallocate these objects when we're done with them. The garbage collector reclaims our discarded objects automatically. But in order to get this, you've got to give up the power of pointers in these languages. You can't read or write outside your data structures or reinterpret their bits as some other type. But since that's a good thing in most applications, a whole class of problems just goes away. But sadly, garbage collection isn't all rainbows. It has a substantial performance cost. It basically has to traverse through all the memory of your program, find all the data structures you allocated at some point, and check whether you're still referring to them from somewhere. This can add noticeable latency and pauses to your application. It's simply not suitable in some contexts, like writing operating system kernels or game engines. But it is a very good trade-off for most end-user applications and websites and even server applications. At this point, I can hear a chant starting in the room. Rust, Rust, Rust. Use Rust. And Rust is pretty amazing. Like C and C++, it gives you full power and control over memory management. But unlike C and C++, it has a strict static checker called the borrow checker that rejects code that is not provably memory safe. So Rust is a suitable language for operating system kernels and game engines, and notably Linux is starting to adopt Rust. It's the best of both worlds in terms of safety and performance. But of course, Rust has to come along with its own costs. Anyone who reads Hacker News or r/programming can probably think of an article or two they've come across about some team that tried Rust and found the experience to involve a certain degree of friction, even if they did succeed, and a great deal of time spent thinking about memory management and how to construct a program that both did what they wanted and also satisfied the borrow checker. This friction can add up over time into higher development costs and lower productivity. So basically, we have something like this. Choose your memory management approach and get 2 out of 3 of these things. Note that I put productivity in air quotes here because C and C++ are productive in the sense that they allow you to ship your code quickly to prod, just not without any safety guarantees. So is there a billion-dollar mistake here? Well, yeah, the obvious one is that the full power of memory management is probably too powerful for most programmers to wield, and we've repeatedly blown our legs off to the point that federal US agencies just recently have released guidelines urging that C and C++ be dropped entirely for new projects from 2026. I also want to add in this section that I think it's also a mistake for most programmers on most projects to be thinking about memory management at all, when garbage collection is perfectly adequate for most applications. Rust is as safe as Java or C#, but it trades off some productivity to squeeze out additional runtime efficiency. Rust is likely to fill a lot of the gaps left as C and C++ become less used for critical software. But for the kind of business applications and web servers that many of us work on, that runtime efficiency, those savings, they're probably a lot smaller than the added development costs of having to think about manually managing memory. So, in summary, there was a problem. I mean, we've got data structures in our programs. They have to ultimately map to memory. So how do we manage that memory? Pointers, super fast, super easy to implement solution, but the consequences, again, here's that theme. They drastically increase the space of invalid programs that are actually acceptable by the compiler because they're semantically valid. It can't detect the errors. The alternatives, well, we've looked at a couple there. Garbage collection and static analysis like the borrow checker, they both provide safety, but they have different trade-offs of their own. Finally, what about our next mistakes? I think we're going to keep making mistakes for a couple of reasons. Firstly, computing is not a natural science. With physics or biology, we can observe nature and get more and more accurate models over time because the physical world is the ultimate validator of our ideas. Computing is just pure ideas based on our own abstract concepts. So we basically have no guide. We just try things out and we keep things that seem to work and we discover the downsides later. Also, in contrast to natural sciences, we rarely bother to back up our claims and opinions with empirical data. I've got books that say a certain architecture or paradigm is better because it's simpler or it's more maintainable, but there are no footnotes pointing to any studies. Simpler and more maintainable compared to what? Based on what measurement? There are a couple of areas where we seem to be in flux right now with competing claims about mistakes. And in the interest of time, I'm just going to mention these really quickly with a single slide each. The first one is error handling. And this is my summary meme slide, so you get the vague idea of what I would talk about if there was time for this. What I find interesting is that the two Spider-Men here are quite adamant that the other approach is a mistake, but they often use the same reasons as the other. It's usually some variation on, well, the other way makes it harder to understand your program's behavior, or the other way makes it easier not to handle errors properly. They can't both be right. But at least they both agree on one thing, and that's Java checked exceptions that were a terrible idea. OOP versus FP would have been another really fun thing to talk about. Is there $1 billion mistake there somewhere? But I actually talked about that here last year. So if you're interested, you can check out that talk on YouTube. But my prediction is that we're going to eventually get to a point where we're going to look back on purist ideas like Java's everything has to be a class as a mistake. Mostly just because it isn't the best tool for every job. And if you're forced to use nothing but hammers for everything, it sometimes takes more time and effort to produce something, and that thing you produce looks like a pile of hammered stuff. The signs are already here, I think. Modern languages are combining OO and FP constructs. Java and C# are adopting a lot of ideas from functional programming, and new languages are finding new solutions to old problems. Think Rust traits instead of inheritance, or structural type systems like TypeScript. And finally, this is the last slide I just threw into this deck because I thought, well, there has to be one, right? In terms of this talk, I think we can say, well, could there be $1 billion mistake here? Yeah, maybe in a few years we'll be going like the $1 billion mistake is the huge cohort of software developers in the world that we just don't need anymore. Or maybe the mistake will be letting the AI write the code, leading to, well, who knows what. But all I want to say, I don't think we have enough hindsight yet to say which is which, but it's another one, obviously, that we're all watching very keenly. So, conclusions. Well, every section had one of these, and you could see that there were a few things that were pretty common, so I've just created a template one here. The problem, it's whatever today's problem is. The solution, well, here's a really powerful way that solves all of that, and it's like really flexible, and it's also easy to implement. But then there's consequences. With enough hindsight, we notice that our solution allows this large class of incorrect programs to be accepted. And all we do is we rely on human manual checks to detect when there's problems. And that doesn't usually go very well. And eventually, we invent better constructs that constrain the design space and provide better static checks. But then these alternatives usually have new trade-offs and new problems. I think if you just want a soundbite, Eric Severy put it nicely when he said, the chief cause of problems is solutions. Also, hindsight is 20/20 is probably apt here, right? Like we see these things with hindsight, but they're well-intentioned in the beginning. No one sets out to make a mistake. So saying blah was a $1 billion mistake is basically the same as saying, in hindsight, there was a cheaper or a better or a safer alternative to blah. Also, software is complex. Most bugs are due to the ability to express bugs easily, often without even trying. The space of programs is huge. Just think of all the valid text files that would represent some program or another. The space of syntactically valid programs is massive, but a small subset of that will be the space of semantically valid programs. And then a tiny subset of that is the space of not only semantically valid, but also bug-free, because semantically valid includes all the buggy programs that you could possibly write, which is a much bigger set than the ones that don't have bugs. And even if you get it down to the correct subset, you still don't know if anyone wants this, Is it actually fit for purpose? Is it maintainable? Is it useful? That little set is what you want to hit, but it's a tiny target in this massive sea of other possible ways you could express a program. So what we really need to do is shrink wrap the design space as closely as possible around the correct programs using the tools of our programming languages, but also no closer, because otherwise good programs become hard to express. As Rico Mariani put it, what we want to create is a pit of success, so that when fallible humans do the obvious thing, it also tends to be the correct thing. I think the idea was also put pretty well in this paper, Out of the Tar Pit. He said, power corrupts. What we mean by this is that in the absence of language-enforced guarantees, i.e. restrictions on the power of the language, mistakes and abuses will happen. This is the reason that garbage collection is good. The power of manual memory management is removed. And finally, don't trust the programmer. if there's one thing you learn today, it doesn't matter that the hole is easily avoided. It just matters that many will fall into it regardless. So try to make good easy and make bad hard. Thank you.
Thank you, Troy, for such a great talk. Let's take it on the floor. Questions, raise your hand, and then the mic will come to you.
What do you think about the role of billion-dollar mistakes being caused less by a solution that is inherently flawed and more a solution that's of its time that becomes harmful when that context is removed? Like, for instance, not having garbage collection was more justifiable back, in the 60s and 70s when they simply didn't have the compute resources to spare, but it became a billion-dollar mistake as we gained those compute resources and still didn't adopt it for these languages.
Yeah, I think it's a great point. When garbage collection was first out there, it would have been a big trade-off to think about, right? Resources are very constrained. Another good example might be if you're in the business of making compilers, one thing that was really important is that they stream your programs. They never basically see the entire context of the source code, and they never have the context of the entire thing that they produce on the other end because there's just not enough memory to have all that. But you probably don't need to worry about that now, right? You could basically have all the text files all fed in at once, all in memory, and maybe even all the outputs all in memory at once as well. So there are constraints that change over time, if that's what you're referring to. Yeah, so I think we just have to sort of keep up with the times and notice which constraints don't apply anymore and which things have now become just so cheap that we shouldn't bother with the maybe more efficient but more error-prone alternatives.
Hello. So my question is, you mentioned C and C++ might be replaced by Rust because of the safety over productivity reason. And do you think that's going to apply to like OS kernels as well, or just like new critical softwares?
To be honest, it's been a long time since I wrote any C++, but it was true what I said in the talk that there's been an advisory recently that, the US government is going to start basically rejecting new projects for government contracts that are written in C and C++. So I think there's going to be a lot of pressure to move away from it. I honestly couldn't answer the more detailed question of how things will go in other, like non-critical fields. I mean, you can be very productive in C and C++, and there's enormous code bases out there. I mean, there's still COBOL code bases running out there, right? So I think they'll be around for a long time to come.
Thanks, Troy. I enjoyed your talk.
Thank you.
Thanks. I was just hoping you could talk more to the functional programming and where you see some of the billion-dollar mistakes in that space.
Yeah, it was something I thought, I would love to talk about that, but I'd probably just do a whole talk on it. To be honest, like the nutshell version of it is that I think both object-oriented and functional programming potentially have their own version of the billion-dollar mistake, which is trying to be too pure. Like if you say everything is a class, now you've got to model everything as a class, and it's not a great way of modeling everything. But functional programming has its own version. In fact, the very foundation of functional programming is the lambda calculus, and the lambda calculus is a calculus that says everything is a function, including the values true and false. They're not values, they're functions that return the first argument or the second argument. So, and everything is built up in lambda calculus from functions within functions. If you tried to actually write a line of business application that way, I mean, it would just take you forever. And in the same way, I think we overcomplicate some of our business applications by trying to figure out how to model everything with classes. So I think probably hybrid approaches are just the more cheap version because we're not being religious or ideological about our code. We're just doing the thing that works easiest. And yeah, that would be my summary.
Hello. Oh, hi. Love your talk. Love your talk last year as well. Got a question regarding that Venn diagram slide. It made me giggle because you had productivity in quotes. Yeah, that one. It's a really good slide. So I wanted to propose the question to you. At what point would you draw the line between like restriction in development velocity versus mistake prevention? Because personally, I'm happy to go a little bit slower if it means I'm not blowing my leg off every other second. So where do you draw that line?
So you're talking about if you have a choice between, say, for example, Rust and C++, right? You're not talking about a choice between Rust and, say, C#.
Abstracted. Just like, okay, so, Java, memory safe, right?
Yep.
But there's a lot of craft in the standard library. There's a lot of craft in just like external user libraries. Building it, pain in the neck, right? So where do you draw that line personally?
I mean, I've fallen down these holes a lot myself, which is probably why I ended up, talking about, being interested in talking about this. Like, I've gone down productivity holes because I'm using languages, and C++ was actually one that got me for the longest. I figured out you could do almost everything in 3 different ways in C++. You could do it kind of the standard normal way. You could do the whole thing in template metaprogramming and have it all run at compile time. And you could do a whole bunch of stuff in macros as well. And what I realized after a long period of time is that I spend so much time not working on the problem that I was originally trying to solve. It's the XY problem. Like, I need to solve X, but in order to do that, I need to solve Y. And I would just get lost in this sea of Y, Z, other things, forgetting all about X. So I would just say that, to me, if controlling the memory was really critical to the application I'm working on, then I'd consider Rust. But if I know that the application I'm working on, which is like an app on a smartphone or a website or something like that, it doesn't really matter even if it's like half as efficient. If I don't have to think about memory management at all, that's probably what I would choose. But if memory is really important, then I think Rust is probably the way to go now over C or C++.
Thank you, Troy. I think we don't have any more questions. Let's give a big applause for Troy again.